So just be a good opportunity just to see, like, does anybody use Asyncio in their current projects? A few. And do other people, are they familiar with Asyncio or know what it is? I see some no's in there as well. Okay, so that's why I I threw a few last minute slides together, which is why it looks very bland. But I'm just going to take a very trivial example of a program. So we've got two functions. They both print something, sleep for a bit of time, and we call it all from a main function. And so this should be very easy to understand the flow of execution. So from main, we call foo function, it prints, sleeps for 2 seconds, comes back, calls bar, prints again, sleeps for 1 second. So this is very predictable. We know exactly what it's going to print, and we know the function is probably going to take about 3 seconds. So obviously you're probably thinking there's ways we could speed this up by doing these in parallel, like, you know, maybe these sleeps are actually doing network requests or something. So your first thought might be to switch to threading. So if we do threading, where we just put the functions into a thread, then our flow of execution can look like this. So when we start running it, it will print foo and bar. These don't render so well on the screen, but yeah, you print foo and bar, then it comes over to here, prints spam and eggs, goes back, sleeps for 2 seconds, while at the same time it's going to sleep for 1 second. So that looks the same as the flow of execution on our previous version, but now it only takes 2 seconds. But because it's threading, we can't guarantee that. So it could also look like this, where we print foo, then it goes to spam, bar, then eggs, so the print changes order. Or depending on how the GIL and stuff works in Python, there is also, yeah, depending on the implementation of Python, it's also possible it looks something like that. At which point you've got all your letters getting jumbled up and you end up with a complete mess. So this is why threads are bad. And you can, I would suggest looking at this, which has a far more realistic example and goes into a lot more about this. So then what we can do instead of threading is go to asyncio. Thanks. So in this case, we've changed our functions to be async. And then instead of threads, we create a task. And then we wait on the 2 tasks to run. And instead of time.sleep, we now have to await asyncio.sleep. So like the threading one, this will take 2 seconds instead of 3. But I can guarantee you the flow of execution looks like that. So it prints foobar. While it's waiting for sleep, it prints spam eggs. So we're back to the same predictable thing that we had on the first run, but it's faster. So that's the basic reason why asyncio was implemented. So now what I'm going to do is take us through a few. I'm going to take a look at a few things as to how asyncio works. I've just realized I'm in the wrong directory, so this is, oh, now I've messed it up. Right. It'll be quicker if you quickly set it up. I just want to change directory to wherever that is, and then run Python again. Thanks. Yes. So yeah, on the left side of the screen, we can see a generator function. So I'm hoping everybody here probably has some idea of what a generator function is, but it's basically any function with a yield keyword in it. And you've probably used those, you probably typically use that in for loop, which I can hopefully do now. I can try. Emacs. Oh. you know where the options are? Problems with borrowing a laptop.
Good question. I'm not 100% sure because I tend to use Vim, not Emacs.
Command plus?
Yeah. Oh, yeah.
Oh, there we go.
I thought I tried that, but it didn't work.
Right. Well, maybe we can do that on here. Yep. Almost it. Okay. So to demonstrate what I was saying, we would use this for x in D1 print x. And then you can see it basically runs through that function and yields each of those values, so 1, 5, and 10. So what I'm going to look at now is some more advanced things that you can do with generators that I imagine some people here are not aware of. Possibly most people, we'll see. But the way it works is when we call the function, we've not run any of the code. What we've returned is a generator object, and this can then be iterated over later. And so the first thing is the next function, which allows you to iterate over this one at a time. So that just runs our generator function to the first yield. We get a 1, and then we can do that again. We get 5, get a 10. And if we do it again, we get a stop iteration exception. And that's actually how a for loop is built. It's literally just calling next on it until you get stop iteration, and then it breaks from the loop. Right, now, for some reason, it doesn't like to order things here, so I need to try and find the second one. There we go. So there's other things we can do with these. If I get number 2. So in this example, I'm going to show you that you can actually send values into a generator. So we can do, I think we want to do next. And next means that we've now run to this yield. So it didn't yield any values, which is why we didn't get any output this time. But then we can do g.send free. And then you'll see it actually started to run the next bit of code. And the x value is now set to 3. So we managed to pass a value straight into that. Also realize you've got slightly more screen estate on my screen than on there. I can't move it. Right. There's 13 examples here, for anybody who's keeping track. 3. So the other thing we can do is we can actually throw an exception into the generator. So if we do we'll do the same thing again. We get to the first yield where we've got x equals yield, but then we can do g.throw, and we can give it, I've done a runtime error there, so we'll do and then you'll see that it starts to run this function again, and then we've put a runtime error in here, and so it's then caught that and printed exception. And then because we've caught that, that means we can run again, and we get complete, and then stop iteration.
Sam, can you possibly zoom in the terminal just a tiny bit?
Yeah, I tried that one. Let's see.
Shift plus.
Command Shift plus. Oh yeah, there we go. Perfect.
You made the window vertically. smaller, like drag it out from the bottom.
Yeah. There we go. Cool. So now if we go on to the next one, difficult to talk and type. So another keyword we can actually use here is yield from. And so if in this example, we do T4. So what's going to happen with yield from is it basically goes into this sub function and it yields from each of those. So after start, you'll see we get sub on the first one, and sub 2, sub 3, then it'll come back out and it runs to the end. And yeah, do feel free to interrupt me if any of this isn't making any sense. So then what we could do is we can actually have we can do 2 generators and then we can basically interleave between those. So in this example, what I've done is I've created a generator that does 1, generator that uses 2, and then you can see we do 1 iteration through sub 1, then sub 2, sub 1, sub 2. And so then you'll see you've got, so you can see we start on 1, then we start 2, get to the middle of 1, middle of 2, end of 1, and then we've got a stop iteration, which is end of my function. Otherwise, we would get to the end of 2 as well. T6. Yeah. I'm about to get to that. Yes, these are some of the more advanced things you can do, but the biggest use is about to come up. But yeah, it's nice to know all this functionality is there. So for T6, we're gonna have a way to sort of manage these generators that we're using. So in this case, we've got sub 1, sub 2, and then we've put it into a loop. So while we've got these sub functions in our loop, we can iterate. We can do like 1 iteration over each of them. And then basically if we get the stop iteration, we know that generator is finished, so we remove it. And then basically that's just going to run until all the generators are completed. So we can run that one. So yeah, so here we don't have the stop iteration because we're now catching it and then removing it. So we run 2, 1, 2, 1, 2, 1. It's a set, so the order's a different way around, but we still do 1 iteration of each time. And then our function ends cleanly. So we can go a little bit further, and here we've got a way to actually add them in as we go. I mean, this is a very awkward way of doing it with global loop, but it keeps it simple for the demo. So basically, our second one, sub 2, when it gets to here, it's going to add it into this set. It's going to add a new subroutine into the set. So then we get. So then when we run it, we're going to end up with 3 in there being run. So if we run that, so you can see we get loop, and then that runs 1 and 2, and then you'll see that that's going to have added it into our generator down here. So on the next loop, we're actually going to have 3. So you get the middle of 1, middle of 2, and number 3 is now being started. And then next loop, 1 and 2 end, and the third one's in the middle, and then the loop, and then we get the last run of the loop where we get the end of the third one. And then I've got one more before I answer that question. So in this one, we're also going to catch our errors here. But so here what I've done is I've created a way that we can stop our generators in the middle. So in this case, so again, I've just done some awkward global just to make this happen, but basically our second one, when we set throw to true, we're going to throw this runtime error, which says, it just says stop. And then what that's going to do is, because we catch the runtime error down here, we then remove it from our set and we just stop running it. So if I import that, I'm on T8, sorry. So yeah, so we'll do like start 1, start 2, middle 1, middle 2. Then you'll see we've printed the catch here, and so we've caught the stop, and that's why we don't see end 3, because we've actually just stopped running that one. But we can also suppress this. So in middle 2, so we get to here. So when we throw that runtime error in, it's going to end up in this yield statement here. So basically, if we did a try except and we caught the runtime error on that yield, then it wouldn't come back to that loop. So it wouldn't be raised down here, which means that it would still end up running. So the actual generator function itself can actually stop you from running it, can stop you from stopping it. So now, back to your question. If maybe a couple of people have caught on by now, but what I've just given you is asyncio, a really rubbish implementation of it. But this is your asyncio event loop. Your async functions, they're just generator functions. When you await, it's actually just a yield. And if you actually used asyncio back in Python 3.4, async await, they weren't keywords, so you literally just wrote it like this with yield from instead of await. So this is how asyncio actually works. And therefore, that's the main use for it. So I'm just going to go over, so now that we understand that, I'm just going to go over some mistakes that I've seen people make in asyncio code, and just some ways that you can optimize code. Where it is 9, there we go. So if you're writing like a web application, you've got your web framework. It might be AOHTTP, Fast API or something. It's an async framework, so you've got to write async functions for your handlers. And then if you write a handler like this, where your fetch is, it might be a database request or something. And in this example, our fetch takes 1 second. So would somebody like to tell me how long that handler is going to take? If the fetch call takes 1 second? 2 seconds. 2 seconds. And if I have 3 requests from a user that comes in at the same time, how long is it going to take for the 3 requests to happen?
6.
Yes. And the problem should be fairly obvious because this is not an async function, so it's going to block. And as we've just said, if you don't have an await keyword, there's no way for it to go back to the loop, which means it can't handle another request. So you've blocked your entire server for 2 seconds. I've seen this in production code, and I've had to fix it all. So yeah, that's obvious. So we move to number 10. I can't find it. There we go. So okay, now we make it async. So knowing what you know, again, this is now async. How long does it take for the handler to do one request? 2 seconds. And how many to handle 3 requests? 2 seconds. And that is because, remember, because our wait does a yield from, that means we are going to wait. That means the second one is not going to run until the first one has completed. So we end up taking 2 seconds to do this. But while it's doing one of those fetches, it can handle another request. So this is a lot better than our previous example. But we can still improve that. T11. So basically, the approach here is we can call asyncio.gather. I can close this now. Yes, we go asyncio.gather. So gather. So remember, if we call these without an await, that like we're just getting the generator object to that point. So we're basically passing our coroutines in async speak into this function, and then we await on this function. This function will basically create 2 tasks that are scheduled into the event loop. So next time the event loop runs, it will run both of them, which means that our handler now takes 1 second. So this is about as good as you're going to get for performance. So we're now running a lot faster. Some other things that that might be useful to you though. There's also a task group, which basically you use it with context managers async with. You create your task that when you do create tasks, that schedules it into the event loop, so it can then be running in the background. When we exit the async with, it will actually then wait on all the tasks in the task group to run. But the main advantage of using the task group is that we can pass the task group in, and then we can actually add more tasks while we're waiting for it to complete. Whereas the asyncio.gather approach, you have to give it everything up front, and it'll only wait on those. So with this approach, you can run through that. I think there was, yeah, it was the 13th. And one other thing that's useful is like maybe if your fetch function is like you need it to fetch something, but you've got other work to do which doesn't depend on it. So you can create your task at the start, do your other work while that's running in the background, and then at the end you can just wait on that task. If the task's already done, it will return immediately without going back to the event loop, or if it's still running, it will wait on it. So I think that is about all I've got. I was just going to point out the documentation. So if you want to do any async stuff, you'll probably end up on this async page, which is not fully on screen. So I'll just say from here, if you go to the bottom, there is a high-level API index. Basically, everything you need should be in there. If you're using anything that's not in there, I hope that you are writing low-level libraries and know what you're doing. But you shouldn't need to use it for a normal web application. And as a last plug, I'm a maintainer of AOHTTP. So if this kind of stuff interests you and you want to do contributions to open source, like speak to me later. We've got a lot of libraries that need maintaining. So, questions or?
Okay, so hi, my name is Lincoln. Some of you might know me from previous talks I've given at Brighton R. So I think I'm the first person to do Brighton Pi and Brighton R. But yeah, so today I'm doing Brighton Pi, and I'm going to talk to you a little bit about climate change and computers. And I was thinking hard about what I was going to talk about, and I thought, I'm going to give you some solutions. But turns out I'm actually not going to give you any solutions. I'm just going to point out some problems. I'm going to try get you to think about some things, and maybe I will hint at a little bit of a solution. And obviously, there's going to be some Python thrown in. And if you know me as well, there's also going to be some Rust thrown in because I can't avoid it. Okay, so just setting the scene of the problem. If we look at like the ICT sector, it turns out that globally it's responsible for 2 to 4% of greenhouse gas emissions, right? So that's just the computers that we use. Data centers alone have a carbon footprint of more than the US commercial aviation industry, right? So usually when we think about climate change, and we think about things that are really bad for the environment, we think about flying, right? This is what the whole like flying less movement is about. Data centers, also terrible, right? So the code that we write and the code that we run has a massive impact on the world's climate. And we're rapidly burning through our remaining carbon budget. And so as we're approaching what could potentially be catastrophic climate change, I think as software engineers and coders, we should be thinking about like, what is our part in this? What part are we playing in this? And how might we be able to mitigate some of these problems and some of these impacts that we're responsible for? So the solution, well, the solution is kind of simple in broad terms. Really, we can use less carbon electricity when we're running our code. We can use fewer computing resources when we're running our code. And we can also just run less code, right? So on a high level, that's pretty simple. But if we dig down, things are starting getting a little bit more complex. So I'm going to talk about the first two things about using less carbon intensive energy when we run our code and using fewer computing resources. I'm not going to talk about the third option, but the third thing there is actually is something that some colleagues of mine are working on, where it's like looking at data processing. So when you process data, this is particularly in the context of neuroimaging data. So I used to be a neuroscientist, now I'm a machine learning engineer. When you process this neuroimaging data, there's kind of standard steps of pre-processing that you do to the data. But do you actually need to do those pre-processing steps? What's the trade-off between doing less pre-processing and data quality, right? So maybe you can actually get away with running less code. So there are people working on that, and I think that's a really interesting idea of just kind of doing less, thinking about what actually needs to be done and not doing stuff that doesn't add any benefit for your data quality in the context of data processing. But like I said, I'm not really going to talk about that. That's just a hint that people are doing that sort of thing. But I'm going to talk about the first two things. So just to set the scene a little bit, kind of one of the things that sort of motivates my thinking a lot about this is this idea that I saw in a tweet a little while ago, thinking about like what we used to do with computers and what we do with computers now. So if you think about when they put people on the moon, they could do it with like the computing power of a pocket calculator and 4 kilobytes of RAM. That was all that they needed to be able to, or the computing power that they needed to be able to do something that was quite a technically demanding feat. But nowadays, we need like 8 gigabytes of RAM just to run a web browser, right? Or probably more if you want to run VS Code. So we have a lot more of those resources, but we're doing a lot less with it. And so why is this the case? So I think what this tweet pointed out is like, way back then, compute was really expensive, right? Computers cost a lot of money, but engineers were cheap. You could get a bunch of really, you could get a bunch of really smart people. You can get them, stick them on a problem, and they could really squeeze the most out of those small resources that they had. But nowadays, computers cheap, right? Inverted commas, when we talk about this cheapness. But engineers are expensive. So it's a lot cheaper to just like throw lots of code, sometimes bad code, at a load of compute, because that can get the job done. And so I really think that there's a couple of, that this is a pretty apt analogy, but I don't think that we should really be thinking of compute as being cheap, right? So maybe in monetary costs, it is cheap, but like I've pointed out, in carbon costs, maybe not so cheap. So I think the idea that compute is cheap is a bit of an illusion. The monetary cost might be low, but there's carbon emissions from energy usage. There's environmental impacts from mining for raw materials, right? So every time a new computer is built, it needs stuff to go in it. That stuff gets dug up from the ground, and that has like massive impacts on the environment. So I think it's maybe a good idea to try go back to how things were and to treat compute as expensive by recognizing the true cost of it, and so trying to minimize that. And I think that we should make engineers cheaper. And so that doesn't mean paying them less. That means getting more out of them, right? So that means that as engineers, we should produce a higher quality product, right? So we should write better code. So these are the two things I think. We should recognize the true cost of compute, and as engineers, we should write better code. So I'm going to talk about those two things, getting more out of your code and recognizing the true cost. So I'll start off with recognizing the true cost. And I'm going to talk a little bit about a Python package that I built as part of a hackathon a few months ago. And this is the Climate Aware Tasks Scheduler, or CATS. So CATS is a Python package that you can use for scheduling compute jobs, so you can take advantage of low carbon electricity, right? So if you need to run something, you might as well run it when the electricity has a low carbon intensity. Turns out, very handily, the UK National Grid provides an API which you can query that will tell you the carbon intensity of the electricity reaching your particular region, and will give you predicted carbon intensities for the next 48 hours, right? And so using that information, if you have a long compute job that you need to run, say you have a 4-hour job that you need to run, there is an optimal time to run that. You can run that now, or you can wait until the carbon intensity of the electricity is lower. And so CATS, the job of CATS is to solve that optimization problem, is to figure out when you should run a compute job, right? So, so that you can take advantage of that low carbon electricity. So CATS is pretty simple in how it works. You give it a compute job duration in minutes, and then CATS queries the API and finds the best time to run it, so that you can have the lowest average carbon intensity of the electricity for the duration of that compute job. And it just outputs a start time, an optimal start time, just to stand it out, which you can then pipe into something else, so like a standard Linux scheduler like @. And it'll also print out some other information about your carbon, the carbon intensity of the electricity, how the average intensity if you were to start the job now versus the average intensity if you were to start the job at the optimal time. So this is just how it works. It's just a simple command. You give it the duration of the compute job and your location, so your postcode, and then it will tell you when the best time to start the job is. And so you can just use a standard scheduler like @. So this will now run the ls command at that optimal time, right? So that's the basic usage of CATS. There's also some other cool stuff you can do. If you give it information about your CPU and GPU, so this is information that you can get off your manufacturer's website, and you give it job-specific information about how many CPUs you're going to use, how many GPUs you're going to use, the duration of the job, memory usage, etc., then it will print out some more information for you. So here's an example of how it works if you give it a config file that has got all that additional information in it. And in this example, I'm actually, you can see I'm just haven't put in a postcode, and it's just geolocating the location of the computer. And And so using that additional information, it can tell me, okay, if I was to run the compute job now, how many grams of CO2 equivalent emissions would I produce versus running the job at the optimal start time, how many grams of CO2 equivalent carbon emissions would I produce? And it gives you a saving, right? And there's also some additional functionality, so you can convert that into like human understandable amount. So, what does that equate to in terms of like flights saved versus, or something like, say, not eating meat for a year, or, miles driven in a car. So those numbers maybe not super meaningful to someone unless they're deep into the climate literature, but you can also get a sort of human readable, human understandable output.
Is that a typical saving?
It really depends on where you are. So here in Brighton, we actually have generally quite low carbon intensive energy. If you're up in Scotland, you do as well. There are other parts in the Midlands where the peak, the max versus the min can be a lot higher. So it really depends on where you are. Yes.
Your runtime not in this somewhere? Start time, this runtime, sorry.
Yeah. So the runtime is just in the job specific information that you give it. Yeah. Yeah. So with CATs, you can actually see the carbon cost of your compute. So you can know. So you no longer have to be fooled into thinking compute is cheap, right? You can actually see what it is, and then you can take a step to reduce it by scheduling your compute jobs at a different time. So if you'd like to contribute to CATs, there's the GitHub. Feel free to check it out, and if you want to contribute to it, contributions are welcome. We've also just received funding from UK Research and Innovation, or we're in the process of getting it. They've said they're interested in funding this. We're just working out the logistics to build this out into a complete task scheduler for high performance clusters, because part of UK Research and Innovation's plan is to have net zero in terms of research conducted in the UK, right? And so the idea is that CATs or something like that can play a part in helping researchers reduce the climate impacts and the carbon emissions from their compute jobs. Okay, so that's recognizing the true cost. The second thing is getting more out of your code. So this is making engineers cheaper by producing high quality code. So Python is great for a lot of things, but energy efficiency isn't one of them. So this is a recent paper that has ranked energy efficiency of different programming languages, kind of normalized against C, right? So you have C as one. Rust is pretty good as well, so I'll talk a little bit about Rust later. C++ is also pretty good. So is Java, at least in terms of energy usage, not great in terms of memory usage. But you can see a lot of money's gone into optimizing JavaScript because it runs the entire web, but Python, not great, right? So that means when we do write Python code, which I'm going to suggest later that maybe sometimes we don't want to only write Python code, but we need to make sure that the Python code that we do write is as efficient as possible. And one of the things that I see as I go around GitHub and look at libraries that I'm interested in using is I see a lot of bad code. And I wish people would write better code. So can we make Python more energy efficient? So I think yes. And the two things that I think we can do is, one is we can partially rewrite compute intensive parts of our Python code in more energy efficient languages, like Rust. And I'll talk about how to write briefly, how to incorporate Rust into a Python package so that you can just call it like regular Python code. But I think secondly, we just need to pay closer attention to runtime's memory usage. So this is like time and space complexity. So this is like the stuff that, a lot of us study for like technical interviews. We learn our algorithms and data structures, and then we forget about it because we think, oh, well, who needs to know how to invert a binary tree, or like who needs to know what like, the O, like the big O of like, this sorting algorithm or that sorting algorithm is. I implore you to actually don't forget about your algorithms and data structure courses that you've done. Remember them because they're important. And I see lots of code where people, if they just picked up an algorithms and data structures textbook, they would have been able to write better code. So writing efficient code, just a brief interlude about my job, is very important for me in my current context where I work, because we run everything in AWS Lambdas, right? Which means that we have very constrained environments in terms of run times, how much compute power we have, and we have like 128 megabytes of RAM as well. So it forces us to think about all of these things, and I think that's a really good habit to get into. Think about, like, don't think, okay, well, I have a pile of compute, I don't need to think about these things. Think about these things, even if you don't need to. I need to, but even if you don't need to, you should think about these things. So yeah, just like I said, things like space and time complexity, we think about these things when we do technical interviews, but we forget about them straight afterwards. I just put a little note, if you haven't come across these terms, there's a link there to a little bit of a cheat sheet which explains what these ideas are in a little bit more detail. Right, but like I said, I come across a lot of bad code in the wild, which could have been solved by just people picking up a textbook. And here's an example. This is some code. This is more or less some code that I found in the wild, simplified a little bit. Now, this code, what it does is it works out a running mean and standard deviation of a list of numbers. So you have a list of numbers, right? That might be 1 million long, and you want to get the mean of, say, the first 2 numbers and the standard deviation of the first 2 numbers, then the mean of the first 3 numbers and the standard deviation of the first 3 numbers, and then the mean of the first 4, 5, 6, 7, 8, etc. Right, and you want to keep all those intermediate results. And how this code was written in this library is essentially like this. So you have your list of numbers, and you're just going to you're just going to loop over that, and each time you're going to extend that list a little bit longer. So you're first going to capture the first 1, then the 2, then the 3, and then you're just going to do working out a sum, and then some sum of squares, and then a standard deviation. So and then just appending that to a list, right? So you might work this out a slightly different way by just using a standard deviation function, but this is actually, if you break it down, if you look at how these things are implemented, this is how it's implemented, right? So it's implemented essentially as a loop inside a loop, right? So now we have a loop inside a loop. And so that's going to be terrible, right? That's just going to, like, as our list extends longer and longer, we're going to be looping over numbers that we've already seen before, right? So once we've, extended our list to 2, right, and we're going to take a mean of those 2, then we're going to add another one, but when we calculate our new mean, we're going to include those numbers that we've already seen. So we're going to, that throwing out and extending our list and looping and then looping again, all of this is going to result in really bad big O, right? So what's the solution to this? Well, the solution is just to pick up a standard algorithms textbook, like The Art of Computer Programming, which is like a classic. Because in volume 2 of that, there is an algorithm called Welford's algorithm, which is actually, which is an algorithm used for working out standard deviations. The advantage of it is that it works them out so that you don't get catastrophic cancellation with, like, floating point. Like, that's the advantage of it. But it works it works like kind of online, right? So you just pass a stream of numbers through a function and apply that over and over, right, to each element. And that's how Welford's works. Now, because Welford's deals with catastrophic cancellation, this is actually, if you go into like SciPy or something like that and you look at their standard deviation algorithm, this is actually how their standard deviation algorithm is implemented, right? because it's a really good way to work out a standard deviation. But it also means that we can totally get rid of like this nested loops that we've had. And now we only have to pass over our list of numbers once. So, so Welford's works, it's just, it just works by applying this function to each element of the list and keeping track of some state, which is then going to be passed on to the next call of the function. So I've just imported accumulate from the editor tools, and then I can just run accumulate with my data and the algorithm and some initial values, right? And so now this is going to apply this function to the first value with these initial values as the existing aggregate, and it's going to take the first value from that as the new value, and then it's just going to do that over and over again, right? So just kind of like standard functional programming kind of ideas of using something like accumulate. So just to make clear what's changed, in the first version we had an outer loop that selected these bits of data, and then we had an inner loop, that list comprehension that looped over each value and subtracted it from the mean so that we could get that standard deviation. So we had these two loops. In the second version, we've replaced our loops with accumulate. And so now we're just taking in that list of numbers and we're applying our binary function, so our function that takes two arguments, and our initial value, which serves as the one argument for the first application, right? And so now we've kind of simplified things a lot, and we're no longer having to have this kind of nested loops situation. Now, I really like this style of programming where this kind of more functional style, which I guess lots of Python programmers don't really use that much. Maybe spend some time learning Haskell, and then you'll get a grip of it. But I think thinking in terms of functional style programming, thinking in terms of streams and applying functions to streams instead of this like style where you're looping, helps you to spot inefficiencies in your code and helps you to spot ways to make your code more efficient. I've actually written a bunch about functional style programming in a couple of blog posts. It's actually in the context of R, but you know, it's as applicable to Python. So how much of a difference does it actually make? So just benchmarking these two, the red line is looking at runtime as you increase the list size. So this is 10,000 numbers. You can see, you know, when you're on these small lists, there's not that much of a difference between these two algorithms. But as you increase, you can see that the original algorithm just shoots up in the amount of time that it takes, where the bottom one just doesn't. It does increase, but only slightly. So it might not seem like much because even at that big set size, it still only takes 5 seconds. But this code, like I said, it's part of a library and it's meant to run on data sets of like 1 million data points. And so in a typical use case, the original algorithm can take over 6 minutes to run on one of these big data sets. And the rewritten version only takes 1.5 minutes, right? So if we think about that difference there, then that difference is quite big. Plus, like I said, it's part of a library, so it could be run thousands and thousands of times. And in that context, if we think about that multiplier, right, that's a huge difference in the amount of compute that's saved, energy that's saved, and carbon that's saved, right? And it could have been done by just, you know, the library authors just picking up standard algorithms textbook. But can we do even better? Because if we're taking 1.5 minutes to run this, and I think we can. And I think this is a really good use case for writing compute-intensive parts of code in another language. So we can take this compute-intensive part and we can rewrite it in Rust. And so Rust is really great for working with Python. The Pyo3 ecosystem makes it really easy to write Python packages that mix Python and Rust. And so you can write Rust functions that you can export and just import straight into Python and call like regular Python functions. So this is what the code would look like in Rust for Welford's algorithm. And if I jump back to the Python version, So that's the Python version. That's the Rust version. Apart from some type annotations, very, very similar code, right? So it's not that much work to actually take that Python code and rewrite it into Rust. They're not hugely different for a simple case like this, right? But it turns out that this is a simple case. Well, actually, so this is how we can then export it as a Python function. So that would be our function signature for that we would actually export, and then this allows us to export it to Python. And then we can just call it from Python just like this. So this package is called py3o demo, and we can just import that running function, which is this function here. And then we can just call it like you would a regular Python function. So you can just pip install it. Once you build it with Pyo3, you just get a regular Python wheel, and you can just pip install that. And then you can start using it as like a regular Python package. So this was a very simple use case. It was just a very simple function, just that one function, that Welford's algorithm. The Rust code and the Python code are very, very similar. In that scenario, you don't get into any of the complexities of Rust because it's a very, very simple bit of code. It's a very constrained thing that you're doing. But it turns out that by doing that, writing that bit in Rust, we can go from 1.5 minutes to 1.5 seconds, right, to do that running average. So just by writing better code, we can go from 6 minutes to 1.5 minutes, and by switching out to another language, we can go to 1.5 seconds. So in that context, 6 minutes to 1.5 seconds, that's a huge difference. And again, this is library code, possibly being run thousands of times. The savings of that, once you think about the multiplier, are actually huge, right? It's a huge saving in energy and carbon. So what's the take-home message? I don't really know. I didn't really plan to give any solutions, but I just wanted you guys to kind of think about these things, to realize that they actually are important. I think it starts by thinking about the impacts of your code, right? Taking these things seriously, thinking about the savings that you can make where you can. I recommend just going for easy wins, right? So the easiest win is if you have big, long compute jobs, use cats to optimize the start time, right? You don't have to change anything about your code. You just have to run it at a different time. But then I also think, refresh your algorithms and data structures, and think about where you can make savings. Don't think, especially if you're writing library code, don't think like, hey, I can just throw it at enough compute, right? Because compute is cheap. Compute isn't cheap. Compute is expensive. We're just, when the climate catastrophe comes, then we'll be paying the cost. So refresh that. And I think a really good way to kind of refresh these things, like no one likes grinding out leak code problems because they can get a little bit boring. But Advent of Code is fantastic, right? Advent of Code, the cool thing about that is each day, so it starts in December, each day they have 2 problems. The first problem is usually on a small data set or a small input, and it's kind of easy to solve. But then the second problem of the day is you get a bigger input, and then you have to change your algorithm because usually you run into complexity issues, right? So on a small data set, it'll work, and then on a big data set, an inefficient algorithm won't work. So it forces you to think about computational complexity and to think about how you can make more efficient algorithms. And it's fun because it has a nice story and you can compete against your friends. So Advent of Code is my recommendation for refreshing your algorithms and data structures. And don't be afraid to dip your toes into other languages where sometimes the savings can be huge, right? And again, Advent of Code is a great way to learn a new language. That's usually what I do when I want to learn a new language. I pick it up and I do Advent of Code in it because it's a great way to learn. So yeah, that's all I'm going to say. I don't really have, much more of a take-home message than that, but just, these things are important, so think about them more.